All right, hey everyone, welcome back to our series on linear algebra. So this time we'll be talking just about matrix algebra. This is section 3.3 in the text. And sorry, that was exciting. Yeah, so matrix algebra, this is going to be very analogous to what we did with vector algebra. Just talk about a lot of properties of what you can do when adding and multiplying matrices and things like that. So we'll get some preliminaries out of the way. This is technically theorem 3.2 that I have written here in the book, but I'm not writing it as a theorem because it's very analogous to the theorem that we saw on the properties of vector addition and scalar multiplication. So I'm not going to prove anything here. We're just going to look at it. Okay, so we start by saying let A, B, and C be matrices of the same size, and then we'll say let C and D be scalars. Then we have the following 8 properties. There's the commutative property of matrix addition. That is, if you add two matrices A plus B, you get the same matrix as B plus A. Now, that may seem obvious, but we're going to see today that we shouldn't take these things for granted. Okay. What else do we have? We've got the associative property for addition. That is if you take A plus B, add them together, and then add C, you get the same thing as adding B plus C first and then adding A. Again, we have to make sure that all matrices in sight are the same size for that to make sense. If you have the zero matrix and you add it to a matrix A, you get A back. And same for if you add A to its negative, A plus negative A, you'll get the zero matrix. That's the additive identity and additive inverse property for matrix addition. Next, we have two properties, left distributivity. Just both of these are distributive properties for scalar multiplication. So if you have a scalar times the sum of two matrices A and B, then instead you could distribute the scalar to each matrix and then add. So CA plus CB, right? Similarly, if you have the sum of two scalars times a matrix, right, you could do each scalar individually times that matrix and then add the resulting matrices together. Those are both distributive properties of scalar multiplication. Then we've got multiplicative associativity. So if you have these two scalars, C and D, you could take D and multiply by A and then take that matrix and multiply it by C. Or you could take the scalars C and D, multiply them together, and then scale A by that number. You will get the same matrix at the end of the day. And then this last one is the multiplicative identity. Just if you scale a matrix by the number 1, that's not going to do anything to the matrix, right? And these are all just direct consequences of the definitions of matrix addition and scalar multiplication, right? Another thing that we can do is take a linear combination of a bunch of matrices that are all the same size. So just let A1, A2, A3, all the way up to AK be matrices that are the same size, okay? Then a linear combination of those matrices is just like C1A1 plus C2A2 all the way up to CK AK, where the numbers C1 through CK are coefficients of the linear combination. So you scale each matrix and then add all the scaled matrices together. That's a linear combination of those matrices. This is exactly the same as the definition for vectors. Notice if I just put like arrows on top of everything. This is the same. This is exactly what we've been talking about with vectors. So the only difference is that we're doing it for matrices. And like we said in the last video, a lot of the rules for matrix multiplication, matrix addition, stuff like that, are going to be generalizations of what we learned about for vectors. Okay, so let's talk about how to take linear combinations of matrices. So we're gonna pick these three matrices, A1, A2, and A3. A1 is 0, 1, negative 1, 0. A2 is 1, 0, 0, 1, and A3 is 1, 1, 1, 1. These three, we're just going to keep coming back to them because Once you've seen one example, you've seen all of the examples, and these three play well together. So the challenge for this problem is to write B, which is 1, 4, 2, 1, as a linear combination of A1, A2, and A3, if possible, right? Well, okay. I have C1, A1, plus C2, A2, plus C3, A3, equals B. This is what I want to do, right? I want to be able to write B as a linear combination of A1 through A3. Well, this gives rise to a linear system, right? I want to write, okay, by the way that matrix addition works, we have to add matrices together component-wise. So what I'm really asking is C1 times the top left entry of A1 plus C2 times the top left entry of A2 plus C3 times the top left entry of A3. I want that number to give me the top left entry of B. That in other words, I want 0 C1 plus 1 C2 plus 1 C3 to equal 1. Now just repeat that with the top right entry. Then that will tell me that C1 plus 0 plus C3 equals 4, right? The top right entry of all these matrices. And then the bottom left entry, I want negative C1, negative 1 C1, 0 C2, and 1 C3 to be equal to the bottom left entry of B, which is 2. And then the last one, I want 0 C1 plus 1 C2 plus 1 C3 to be equal to the bottom right entry of B, so 1. Look at that, it's a system of linear equations. By the way, this is precisely the same system of linear equations that you would get if you were to just pretend that A1, A2, and A3 were vectors in R4, specifically where you go like where the entries go in increasing order across the rows, like we did. The first entry, the second entry, the third entry, the fourth entry, like that. That's easiest to see if you look at the coefficients in this middle column. It's 1, 0, 0, 1. Yeah, 1, 0, 0, 1. Right. And as long as you do it consistently, you could have done this in any order. It would have given the same system, but maybe the equations were given in a different order. Right. So in other words, trying to find a linear combination, trying to write a matrix as a linear combination of other matrices of the same size is the same as taking those matrices, all the matrices in sight, and just pretending like they're vectors, and then doing what we know how to do. But like we're not done. We have to like actually do this. So how do we solve problems like this? I recommend Gauss-Jordan elimination, and I'll write down the augmented matrix 0, 1, 1, 1, 1, 0, 1, 4, negative 1, 0, 1, 2, and 0, 1, 1, 1. I'm not going to row reduce this one live, but notice the row reduction is not so hard. If you put it in reduced row echelon form, the final matrix, it's going to look like 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, and 1, negative 2, 3, 0. Okay. If you're uncomfortable with reduced row echelon form at this point, you should pause the video and row reduce this matrix. It may not be fun, but it's an important skill. Okay. When we do this, we see that C1 is equal to 1, C2 is equal to negative 2, and C3 equals positive 3. In other words, a1 minus 2a2 plus 3a3 equals b. And again, you can verify that. Just actually do the linear combination, right? Actually compute it. So if we can compute linear combinations of matrices, then we can also talk sensibly about the span of a set of matrices, right? The span of, let me underline that. The span of a set of matrices of the same size, of course, is the set of their linear combinations. So we want to go and describe the span of these same three matrices, A1, A2, and A3. Okay. The way that we do that is we say, okay, let W, X, Y, Z be a matrix in the span. Okay, then W, X, Y, Z is a linear combination of these three matrices. And so we have the same linear system that we had before. C1, oh, sorry, I already read it wrong. C2 plus C3 equals not 1, but W. C1 plus C3 equals X minus C1 plus C3 equals Y, and C2 plus C3 equals Z. Okay? This system of linear equations has augmented matrix 0, 1, 1, 1, W, 1, 0, 1, X, minus 1, 0, 1, Y, 0, 1, 1, Z. Okay, row reducing this is a little bit, you should check this carefully. But when you do, you'll find, okay, one, you'll have, ones on the first three leading entries, zeros everywhere else. You'll have a row of zeros at the bottom, and then some other functions of W, X, Y, and Z up here, with the most important one being this bottom one, W minus Z. Notice if you subtract this row from this row, whatever, if you subtract these two rows in the bottom, you'll get that row of zeros, but you'll end up with like W minus Z or Z minus W or whatever. Okay, so, and then the other ones, I'll just write the other ones, although I'll have to copy them. It's 1/2 X minus 1/2 Y. Negative 1/2 X minus 1/2 Y plus W. And then 1/2 X plus 1/2 Y. So these first three equations give you a recipe in terms of W, X, and Y for how to extract the coefficients or how to extract what numbers you need in order to write any matrix in the span of these three matrices as a linear combination of those three matrices, right? That last equation, though, notice it's the only equation that has Z, and for this, we know that this system must be consistent. So that last equation has to be a row of all zeros. In other words, W minus Z has to be equal to 0. So Z has to be equal to W. And then, if you know that Z is equal to W, then what we've been told is that if you just give me any W, X, and Y, and then I'm stuck with Z has to be equal to W, like Z has to be equal to W again, then this the top three rows give you a recipe for how to use the coefficients, or what coefficients you need to use in order to write that matrix that you've handed me as a linear combination of the original three matrices. Which means we can describe the span now. It's this the span is I'm allowed to choose any three coefficients that I want, or any three entries that I want, and then the fourth one is forced on me. So we write it like this. The span of, I'm just going to put A1, A2, and A3. We just say W, X, Y, W, like this. Okay. Maybe we'll put curly braces so that it looks like a set, right? It's the set of matrices which have anything in the first three entries, and then the last entries, the bottom right entry is the same as the top left entry. For that reason, if we had, like, for example, if we had known this and we were just asking the question, is B, which, if you remember, was 1, 4, 2, 1, we were asking, if we were just asking, is this vector a linear combination of A1, A2, and A3, we could have just looked at this matrix form and just asked, well, does the top left and the bottom right entry match? Sure enough, yes, they do. So we automatically know that this is a linear combination. Linear combination of A1, A2, and A3. And if we had our hands on this matrix, we could have just plugged in W, X, and Y into those top three equations, or top three expressions, to extract the coefficients. And you can go ahead and do that if you'd like. It's going to feel a little bit repetitive. But yeah, but that will tell you exactly what coefficients you need in order to write B as a linear combination of A, B, and C. Sorry, of A1, A2, and A3. We also could say, 1, 2, 3, 4, or whatever, 2, 4, 6, 8, doesn't matter. We know that one's not a linear combination, because look, the top left and bottom right entries don't match. So, okay, we can talk about span, we can talk about linear combinations, then we should probably be able to talk about linear dependence versus linear independence, right? Of matrices, not just of vectors. So the definition for linearly dependent matrices is the same for that as that of for linearly dependent vectors, right? Namely, if you have matrices A1 through AK, those matrices are linearly dependent, all the same size, of course, right? Those things are linearly dependent if there is a non-trivial solution to C1, A1 plus C2, A2, blah, 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 all the way up to CK, AK equals 0, the homogeneous system, right? So, and linearly independent if the only solution is the trivial solution. So the question is, are these guys linearly dependent? In other words, can we write 0 as a non-trivial linear combination of these three matrices? In other words, so we know that the 0 matrix is definitely inside of the span. Of these three matrices. But the question is, when you make the homogeneous system, which I'm going to skip writing the system and I'm just going to jump right to the augmented matrix. It's the same one that we had for all the other ones. 0, 1, 1. Now 0, we're trying to write 0, 1. We're trying to write the 0 matrix as a non-trivial linear combination of these three matrices. So 1, 0, 1, 0. -1, 0, 1, 0, 0, 1, 1, 0. Does this system have a non-trivial solution? We know that the system is consistent because it's homogeneous. It will always have one solution, namely the one where you set all the coefficients equal to 0. The question is, does it have any others? Remember from our theory about vectors that if it has one other solution, it will have infinitely many solutions. That means it will, and that's because it will have a free variable, which means that the reduced or the row echelon form of this matrix has has non full, I guess full rank. I'm not allowed to say that yet. We're gonna need two free variables. That's by the rank theorem, right? The rank is the number of rows that have leading variables. In order to get a free variable, we're going to need 2 rows of zeros in the reduced row echelon form. But remember, when we row reduce this thing, we end up with just this matrix, the one that has the 3 ones on the diagonal and zeros everywhere else. No free variables. Meaning that the only solution is the trivial solution. So A1, A2, and A3 are linearly independent. Okay, good. Great. So now we get to talk about, so far everything is exactly the same as vectors, and it feels like everything is almost the same as just with numbers. But I have to tell you, the rule of thumb. So I mentioned earlier in this video that we shouldn't take these things for granted. Just properties of addition, multiplication. So here, so I want to tell you about this rule of thumb, which is just don't assume that things are going to behave like real numbers. I'm going to give you 3 examples on this slide of how that's going to just break down horribly. So here I've got 2 matrices, 3, 9, -1, -3, and 0, 1, 2, 3, innocent 2x2 matrices. I've multiplied them together, and then I've switched the order of the product and multiplied them again. And I've written that they're equal, and you would just assume, yeah, 2 numbers, 4 times 5 is 20, 5 times 4 also 20. So surely multiplication commutes. Let's investigate. Okay, the left-hand side. 0, okay, so remember that the way that this works, the way matrix multiplication works, is we take the columns of the second matrix times the rows of the first matrix. And whatever row you're in is going to be the row, we do a dot product of those rows and columns. That dot product will give a number, and that number will be the ij entry in the product matrix, where I is the index of the row and j is the index of the column that you used. So here I've got the first row in the first column, which means that it'll be the 1, 1 entry when I'm done. The dot product of those 2 vectors will be the 1, 1 entry. So 0 times 3 is 0, 2 times 9 is 18, 0 plus 18 is 18. Then let's do the one below it. So 0 times -1 is 0, and 2 times -3 is -6. Then let's do the top right entry. So 1 times 3 is 3, 3 times 9 is 27, 3 plus 27 is 30. And then 1 times, we'll do the last one. So 1 times -1 is -1. 3 times -3 is -9. -1 plus -9 is -10. So apparently the product of these two matrices is 1830, -6, -10. And now all we're going to do is switch the order and do the matrix multiplication again. I'm going to do this one faster. You should get to a point in this class where you can do these like mental math, okay? Probably by the end of this week, that's where you're going to want to be. So let's go. We're going to do, I'm just going to go the same order, okay? I don't know why I fill the columns, but it just is what I do. That's what I learned. Okay, so 0, 3, 0, -1, -1. 3 times 2 is 6, -3 is 3. 9 times 0 is 0, -3 is -3. And 9 times 2 is 18, -9 is 9. That's an interesting output. It seems to have reversed the rows in the second matrix. But certainly, wait a second. What's going on here? These matrices aren't even close to being the same. And in fact, they're just not equal. We switched the order of multiplication and did not get the same output. In other words, matrix multiplication does not commute. That is something that we'll have to wrestle with. We have to throw away that notion completely. Let's try another one. Let's try squaring this matrix, the first one that we had. 3, 9, 1, -3. So let me just write that for you in a way that's very easy to look at. 3, 9, -1, -3 times 3, 9, -1, -3. The output for that, the first row is going to be 9 minus 9 is 0, or the first entry, sorry. Then beneath that will be -3 plus 3, which is 0. Then 27 minus 27, which is 0. And then -9 plus 9, which is 0. Wait a second. I had a non-zero matrix squared, and it gave me the zero matrix. In other words, for real numbers, if you had some real number and you squared it and you got the number 0, okay, that definitely implied, like, what number times itself is equal to 0? You know that the number is 0. However, I just squared a matrix that was definitely not 0, and I got the 0 matrix. So for matrices, a squared equals 0 does not imply that a equals 0. Right? So again, we can't just assume that matrices are going to behave like real numbers. Let's mention briefly Theorem 3.3, which basically tells us that when we can what we can assume about matrix multiplication. This theorem is stated kind of in a funny way. It says let A, B, and C be matrices whose sizes make sense, and let K be a scalar. When I say matrices whose sizes make sense, I mean, like, don't go multiply a 2 by 3 matrix by another 2 by 3 matrix. Remember, the inside numbers have to match in order for matrix multiplication to even be defined. So pretend that for all the stuff that we're going to write down, the sizes work out, right? Because otherwise it doesn't make sense to write these statements anyway. Okay, matrix multiplication is associative. If you multiply two matrices and then multiply on the left by a third, you could have multiplied by the first two and then multiplied on the right by the third. Okay, matrix multiplication is distributive. So it's left distributive and right distributive. If you add two matrices and then multiply, you could have just multiplied each matrix separately and then added the result when you were done. And that's whether you're multiplying on the left or on the right by a matrix. Scaling, so if you scale the product of two matrices, you could have scaled one or the other one first and then multiplied those two matrices, and you would have gotten the same output. This one is not too bad to prove. And then the last one is, okay, this is very stated kind of strangely. If A is an m by n matrix, then the rows, okay, let me just put m by m and then m by n. If you want a multiplicative identity, then the identity matrix of the right side, like the size of the side that you're multiplying it on, will do the job. So if you take the m by m identity matrix and multiply it on the left of A, some matrix which is m by n, you will get the original matrix back. Remember, the identity matrix is the one that's ones everywhere and zeros everywhere else. I don't know why I did 5 by 5, geez. Okay. Yeah, that's the identity matrix, where m is the number of rows that A has. That, if you multiply it by A, will give you A back. And if you multiply on A on the right by the n by n identity matrix, notice again we have m by n by n by n. These match, and these make up the dimensions of the resulting matrix, and it's the same size, right? Okay, great. So think about the perfect square binomial property of matrices. We have to ask, is this true? Like, does this hold? Remember, matrix multiplication doesn't necessarily commute. So what we have to do is like write this. We have to do this very, very carefully. Well, by definition of like the matrix power, right? Something being squared. This is A plus B times like the matrix A plus B times the matrix A plus B. Well, by left distributivity, if I have some matrix times the sum of other, if I have a matrix times the sum of two other matrices, I can distribute across the sum. So really, I can write this as, take this as a matrix and distribute it. So I'm getting A plus B times A. Notice the A stayed on the left when we did this distributive property. In fact, this is called left distributivity for that reason. So we have A plus B times A plus A plus B times B. And now by right distributivity, I can distribute these A's and this A and this B. So I can write this as A times A. I'll just write it AA plus BA. That's the first distributive property. Then the second one is plus AB plus BB. Now, by definition of matrix power, this is A squared plus AB plus B squared plus BA. I snuck the commutative property in there, but remember, from the very first thing that we wrote down in this video, addition does commute. Multiplication doesn't necessarily, but addition does. Now, what I want to do is set this as being equal to A squared plus 2AB plus B squared. If I were to subtract A squared, B squared, and 1AB from both sides, I'm left with the result that AB equals BA, which is the commutative property that we know and love. However, this equality is contingent on this equality. That's what we're saying. They're equivalent conditions. So the property that we want, the perfect square binomial property of matrix powers, or sum of the sum of two matrices, holds if and only if those two matrices commute multiplicatively. So yeah, it only holds sometimes, and part of the art is figuring out when do two matrices commute, right? There are some cases where it does, sometimes it doesn't. So yeah, we'll have to it's something just to keep in mind moving forward. Whenever you're about to multiply two matrices together, don't assume that the product commutes. Okay, great. By the way, if you try to multiply two matrices, which are not square, and then you try to commute the multiplication, even if you get something well defined, so for example, like a 3 by 2 times a 2 by 3, oops, yeah, um, if you switch the order of that product, one way is going to be a 2 by 2, the other way will be a 3 by 3. Yeah, uh, you have to check the dimensions and the properties of matrix multiplication. I think the way I have it written here is going to be a 3 by 3, right? But if you switch the order, then it will become a 2 by 2. And one way you'll be dot producting vectors of length 2 to get a 3 by 3 matrix, and the other way you'll be dot producting or multiplying using the dot product vectors of length 3 to get a 2 by 2 matrix. There's a lot of cool symmetry, but the properties of matrix multiplication are not those that you would expect. Speaking of properties, let's take a look at some properties of the transpose of matrices. These again are kind of just not what you'd expect. Some of them are obvious. So remember that. First of all, let's just state the theorem, which is that let A and B be matrices whose sizes make sense, and let K be a scalar. Then we have all these different properties. Now, remember that the transpose is the thing where if you were to write A using double subscript notation, Aij, like this, then A transpose is the thing that you get when you switch the rows and columns. So Aj. Okay, yeah. The Ij entry of A becomes the Ji entry of A transpose, right? It's the one where you flip it across the main diagonal. Well, okay, let's look at the first property. The transpose of the transpose is the original. That makes sense, right? Because if to get to the transpose, you flip the rows and columns of A, well then flip them again. You'll get back to where you started from, right? Same thing if you were to scale the transpose, that's like multiply the transpose by a scalar multiple. That's the same as multiplying the original matrix by a scalar multiple and then taking the transpose. So that these make sense. One property that's really handy is that if you take a square matrix, and raise it to the some power, any power for r greater than or equal to 0, and then take the transpose, you could have actually taken the transpose first and then raised that other matrix to the r power. You'll get the same matrix. So this one is a little bit less obvious. Okay. Here's something that's crazy, which is that if you take two matrices, add them together, and then take the transpose, you could have taken the transpose of each one separately and then added them together. That's also less obvious, although it does kind of make sense once you think about flipping on the main diagonal and stuff. But here's the least obvious one, this fifth property, which I've starred. If you multiply two matrices and then take the transpose, the thing that you get is not the transpose of the product, but it's the transpose of the product. It's the product of the transposes in reverse order. You have to like switch the order of multiplication, but also transpose both. And then when you do it, you always get the same matrix back. This is kind of surprising. And we're going to prove that one. There's a proof in the book as well, but this is like the least obvious one, but it's also kind of the coolest. Okay, so first thing I want to do before in this proof, the first thing that we want to do is make sure that the dimensions work out, right? Because we're about to take some products and show that the products are equal. Well, okay, suppose that A is m by n and B is n by r. Notice notice that the columns of A and the rows of B have to be the same number. Number of columns and number of rows has to be the same in order for the product to even make sense. And then when that product makes sense, the output or the product matrix AB will have the number of rows that A has and the number of columns that B has. So it will be n by r. Okay, if you transpose A, you get an n by m matrix. And if you transpose B, you get an R by N matrix. If you then do B transpose A transpose, then you're doing an R by N matrix, that's B, times an N by M matrix, that's A transpose. So B transpose A transpose. What is the dimension, the expected dimension? It's R by M, which is the same as the transpose of this thing. Remember, transposing a matrix will flip the rows and the columns. So it will flip the number of rows with the number of columns. So if AB is n by r, AB transpose is r by n. Fortunately, that's precisely what B transpose A transpose has as its dimensions, r by n. So at the very least, AB transpose has the same size as B transpose A transpose. Now, how do we know that they have the same entries? Right, I mean, at the very least, this is kind of like, it's a good start. How do you know that the entries are the same? Okay, so for that, we actually need some extra notation. What we want to do is, for a matrix, if you have a matrix, we'll call it matrix X, whatever. We're going to denote row I like this, row I of X, and column J as col J of X. Okay? So now we ask, what is the IJ entry of AB transpose? That is what we're going to do. And we're going to show, is that the same as the IJ entry of B transpose A transpose? That's what we want to know, right? So just pick an arbitrary entry inside of AB transpose and figure out what it is. Okay, well, so first of all, first thing we need to notice is that the IJ entry of AB transpose is the JI entry of AB. That's what the transpose does. This is like the definition of the transpose, this equality. It just says that the IJ entry of the matrix is the of the transpose is the JI entry of the original matrix. Well, what is the JI entry of the product of A and B? Well, that's just the dot product of the jth row of A and the ith column of B. That's all. It's a dot product. You just go to row J, you've got A, go down to row J. And then you got B, which, has the right number of rows and columns, whatever. You go over to column I. I guess got to make sure that sizes work out. Whatever. Okay, great. then you do the dot product of those two things. That is precisely the ji entry of the product AB. But right here, notice that row j of A is the same as column j of A transpose. That you can see by just oh wait, I need a row of A. I want to flip across the diagonal of A. What that's going to do is produce for me a column inside of A transpose. Okay? And if you know however many rows you had to go down to get there, you have to go over that many columns to get there in the transpose. So row j of A is column j of A transpose. And for the same exact reason, column I of B is now row I of B transpose. If you just transpose B, this column flips to become this row. Whatever. Looks like the second row or something like that. Of the transpose. So the matrix flips to be something like this. And we just did its column. Or we flipped a column into a row. Okay? So this is just, again, the definition of the transpose. And we're just keeping track of what happens to any given row or any given column when you take the transpose. Okay. Sorry, I'm just making sure to leave enough space when I'm going through this explanation. We have a nice trick here. Now notice all I did was switch the order of multiplication. I switched the order, right? Row j, column j of A transpose times row I of B transpose is row I of B transpose times column j of A transpose. Now you might think, wait, you just got through saying multiplication doesn't commute. But this dot is a dot product, right? That was what we said. In order to define the ji entry or any entry inside of the product of two matrices, you have to take the dot product of the corresponding rows and columns. So it's a dot product. And the dot product commutes. U dot v is v dot u. We proved that like a while ago. Yeah. And so we get to use that fact right here to use this to commute that multiplication. And now we just ask. So I have row I of B transpose, and I have column J of A transpose being multiplied together to give me, that's the dot product of a row and a column of two matrices, which means it's row I and column J, which means it's the ij entry of the product of those two matrices written in that order. So in other words, this expression is precisely the ij entry of the product B transpose A transpose. All of these things are equal, which means that the ij entry of AB transpose is the ij entry of B transpose A transpose. That's what we were trying to show. And so we're done. These matrices have the same entries. Yeah, it took that was a lot of work to prove this strange property. But apparently taking the transpose of the product is like taking the reverse order product of the transposes. Kind of an amazing fact. Speaking of amazing facts, I want to end with a very beautiful theorem. We won't prove it. It's mostly just an observation and a fun thing to end on. So it says that for any square matrix, whatever, if you take that matrix and add it to its transpose, you will automatically get a symmetric matrix. A symmetric matrix is a matrix where a matrix M, where if you take its transpose, you regain the original matrix. Let's look at that. So here I have the matrix 1, 2, 3, 4. its transpose is 1, 3, 2, 4, right? Flip it across the diagonal. And it has to be a square matrix. What you end up with is, okay, if you flip it across the diagonal and then you add them together, you end up with a matrix which is symmetric. Notice if I flip this one across the main diagonal, the 2 and the 8 stay put and the 5s switch. But switching 5 with 5 doesn't change the matrix, right? And so this is symmetric. Look at number 2 for this theorem. For literally any matrix that you want, if you take the product of it and its own transpose in either order, you'll get a symmetric matrix. So here I've got a 3 by 2 matrix and a 2 by 3 matrix, kind of like what we were looking at before. I'll spare you the details of actually working out the product. But notice, let's just do the dimension counting. This is 3 by 2, and this is 2 by 3. The insides match, so the product is well defined. The outsides dimensions give us the dimensions of the product. So 3 by 3. And look at, flip this on the diagonal. The 1, the 5, and the 9 stay. The 0, the 2s, the 0s, and the negative 3s all switch with each other, but all of them matched their pair on the opposite diagonal. And so you end up with the original matrix. Or you end up with this product matrix when you're done. When you're done trying to take the transpose. Okay, and then if we did it again, this is now 2 by 3 and 2 by 3. Sorry, 3 by 2. The 3's match, and the 2's give us the dimension of the output, and once again, symmetric. Just for some context, it is not necessarily true. So, okay, we said for literally any matrix, A transpose, and A transpose A are symmetric. But suppose I had 2 symmetric matrices and I multiplied them together. It's not necessarily true that those things are, that the product is symmetric. So if I had A and B symmetric, it's not necessarily true that AB is symmetric. Remember that symmetric matrix has to be square, right? So that's implicit here. Because, right, if you're going to transpose it, the number of rows and number of columns switch, so it has to have the same number of rows and columns already. So if both of these are symmetric, they must also be the same size, square matrices that are symmetric. You take their product, it's not necessarily true that the product is symmetric. I challenge you to come up with an example for that proves, that of a product of 2 matrices which are both symmetric, but whose output is not symmetric. And that's actually where we're going to stop this video. So next time we'll pick up with section 3.3. We'll start talking about matrix inverses. We're going to get pretty wild pretty quickly, but I will see you in the next video.